Hi, my name is Chris Barton, and this is my final presentation for natural language processing at DePaul University. For my final project, I decided to look at vector semantics. Vector semantics, or a vector space model, is a way of representing text data in a mathematical form. This has many use cases such as word similarity, clustering, and dimensionality reduction. For word similarity, there's both first order and second order. First order refers to words that frequently appear next to each other, such as how to, how come, and so on. Second order refers to words that can often replace each other, such as additionally or furthermore. Clustering, which we're all probably familiar with, could be used to find similar documents within a corpus of documents. And dimensionality reduction could be used for extracting themes. More specifically, we could use LSA or SVD. For this project, I chose to experiment with two different ways of discovering similar words. I chose to look at both first order and second order. For first order, I chose to use a word to context matrix and using the similarity scores PPMI, or pointwise mutual information, and Jaccard similarity. For second order word similarities, I decided to implement Brown clustering, which is an HMM-like hierarchical clustering algorithm. To find first order word associations, I choose to use the word to context framework. The goal of a word to context matrix is to enable us to find similar words. Here, essentially, it's an M by M matrix where M is the size of the vocabulary, and each cell contains the count or other score for how often a word occurs with another word. Typically, a co-occurrence is defined by a windowing function around, maybe plus or minus 2 words around the current word in a document. The smaller the window, the more syntactically similar the words will be, and the larger the window, the more semantically the words will be similar to each other. So once we have the M by M matrix, we can then transform it and calculate a different score that is probably more applicable, such as pointwise mutual information or Jaccard similarity. For the specifics of my project, I chose to look at search query data that was provided by AOL in 2006. This was strictly for non-commercial purposes. So what I did with this is I downloaded the data, and since the data set was quite large, it was about 35 gigabytes, I had to use the Hadoop framework, and I was able to import the data to Hadoop, and then cast some tables over it. And for context, I just used anytime a word was in the same search query as another word, I counted that as a co-occurrence. What I did then was calculated the total count of word A and word B and the count of them together. At this point, I was able to then calculate both pointwise mutual information and Jaccard similarity to come up with a score for how often or how similar a word is to another word. After the program was complete, I ran it and then computed the output. And on this next slide, we can see an example of for word A, how, and then for word B, how similar the word how is to another word. So for example, how install, how cable, how many, how to, how lose. And then we see the count for A, B, and the intersection of A, B. And then we see both the pointwise mutual information for the two words and the Jaccard similarity. If we take a closer look at pointwise mutual information and Jaccard similarity, we can see that they're fairly correlated. However, it seems to me that Jaccard similarity does a little bit better of a job, specifically if we look at how to, which to me, if I look at this list of words, that seems to be the most obvious to me. The Jaccard similarity is quite high. However, these other words have a low Jaccard similarity, but a higher pointwise mutual information. So based off of kind of the insights from this slide and from inspecting other scores, it seems like Jaccard similarity might actually be a slightly better score when looking at word similarity. Next, I decided to implement Brown clustering, which was proposed in 1992. The goal of Brown clustering is to find second order word associations, so words that can be used to replace each other. The idea is to input a whole corpus and then to output a hierarchical clustering that matches similar words to each other. More specifically, I can walk through the details outlined here. So the step one is to read in the corpus. Next, you would want to create a dictionary of words and how frequently they occur. then sort that dictionary from highest to lowest. After which you'll want to take the top M words, which could be anywhere from 50 to 1,000, depending on how large your corpus is, and then look at all of the possible permutations of those top M words. Once you have all possible permutations, you then calculate the perplexity of each particular permutation. Then you'll look for the perplexity that has the highest perplexity and merge those two words. So for example, if we take in the top 50 most frequently occurring words, we might find that the highest perplexity is for the words, for the merge, maybe for the words how and to. Next, you'll want to append 1 to the original set of M words and rinse and repeat until you are left with no other words. That will result in a merging that results in one cluster, and then it'll go all the way down to individual words. This next slide is an example of a toy data set I created with 2 sentences about a cat and a dog and a mouse. Here we can see the output of the Brown clustering algorithm. The output can be visualized as a tree diagram where each split takes on either a 0 or a 1. In this particular instance, all splits to the left take a 0 and all splits to the right take a 1. So we can look at this tree and kind of map down. We can go 0 and then 1, and we see that both dog and cat are grouped in the cluster 0, 1. And then it goes all the way down to 0, 1, 0, which could be the dog cluster. So overall, just based off the toy example, which was only 2 sentences, it already is picking up on similarities for dog and cat, which could, be thought of as second order word associations. During the implementation of this algorithm, what I did was I had a nested list of tuples. So actually implementing the Brown clustering algorithm wasn't extremely difficult. However, when I ended up with a list of nested tuples, I found actually parsing them out to get this tree structure and these bit strings to represent the clusters was fairly challenging for me, as I'm not implementing tree searches. What I ended up doing was doing a depth first search, I suppose you would call it. So I'd split, the left and the right, and then go down all the way to his, and then kind of reverse back until I make it to the top of the tree, and then kind of rinse and repeat with the same kind of formula for the left side of the tree, or the right side of this tree, excuse me. Overall, I thought this was a pretty interesting final project. Both the Brown clustering had a lot of learnings in terms of kind of just programming an algorithm from scratch, and I think I found some interesting insights with the word to context, especially around the differences between pointwise mutual information and Jaccard similarity. Moving forward, I think there's several next steps I could take to kind of enhance kind of both approaches. For the word to context, I think we could look at maybe using a weighted combination of both pointwise mutual information and Jaccard similarity to come up with a final score. For Brown clustering, I think we could look at using parallel processing to calculate the perplexity of all permutations. This could bring down the complexity to OV times n plus n, which the implementation I had was V times n to the power of 2 plus n, which even that one is a faster implementation than the naive implementation, which is V to the power of 5. Finally, I think there's a way to kind of combine both word or Brown clustering and word to context by taking the top or the highest scored words and kind of tokenizing those as a bigram that we could use to cluster. And for example, with Brown clustering as it stands, New York City would all be 3 individual words. However, if we had a score that indicated that these almost always are grouped together, and we see a document or a string that has these 3, we could go ahead and group these together from the get-go. Therefore, New York and City might, all go to different clusters in the naive implementation. However, in this new implementation, they would go together as one word. So that is it, and thank you for taking the time to watch.